So this video is going to walk through this lab where we're going to introduce the HEC-RAS software. HEC-RAS is sort of the industry standard for most open channel flow modeling work. It's developed by the Army Corps of Engineers, and it can simulate steady and unsteady flow, uniform flow, and both rapidly and gradually varied flow. There's a lot you can do in this program, and this is just kind of a brief introduction to it, to run one steady flow simulation in a pretty simple channel. The problem we're going to be modeling here is described. We've got two channel cross sections that are given. One is upstream of the other. You can see the elevations here and then the station offset from the channel center. So we've got a lower cross section here. It's lower elevation, so it's downstream, and then an upper one. And they're located at River Station 1000 and River Station 0, which are 1,000 feet apart. And I'll talk a little bit more about station and river station in a moment. We've got a development where we've got existing peak flow of 20 CFS, and development's going in, it's going to increase the flow to 100 CFS. So we've got some data here, Manning's ends, contraction expansion coefficients. We're going to be entering all this data into the program in just a minute. If you look at the next page of this lab handout, everything I'm going to be going through is basically listed step by step here in these couple pages, but the video will help you see these things in action so you don't kind of lose where they are. And there's a couple little notes that will be helpful if you're going through the video as opposed to just looking at the handout. So you're going to open HEC-RAS. What opens is just this simple window right here, and it says start a new project. So file, new project, and I'm just going to call this lab 6. Hit OK. Sure. One note is later on you may want to make sure that you're saving this in, say, like your own personal sort of Z drive or some drive that has a drive letter on it. If this starts with like a couple slashes and then a server name and then maybe your username, it doesn't have a drive letter at the beginning, you might run into problems later when you go to run the model. But I'll mention that again later on. So if you're running into errors and you have no idea why, that could be the issue. Okay, so we're going to hit the View Edit Geometric Data. That's this one right here. And we're going to start with a reach drawn upstream to downstream and add two cross sections. So we're going to click on River Reach right here. And all we're going to do for this one is we're going to click, and we're going to click, and we're going to double click to end that reach. Okay? Just a vertical line. We're drawing from upstream to downstream. So this reach is going to be flowing down the way I drew it. You can name the river whatever you'd like. I'll call this River Lab 6 Reach. We'll call it, oops, what happened? Reach 1. So a river can be made up of multiple different reaches, and each reach allows you to change what the flow rate is into that reach. In this case, we're just going to have one reach, so it's very simple. And when you hit OK, it should look something like this. And then we're going to add the two cross sections. So we're going to hit the cross section editor over here. And the first thing we're going to do is we're going to go to Options, Add a New Cross Section. It says enter a new river station for the new cross section. So HEC-RAS uses two terms, river station and station. River station is where you're at along the reach, right? So at the most upstream extent, you're at a given river station, and at the most downstream extent, you're at a different river station. River stations are numbered, they're numbers, and they go in decreasing magnitude as you go downstream. So in this case, we've got two river stations in what's given in our cross sections. One is river station 1000, one is river station 0. River station 1000, that's a bigger number than 0, and it's upstream from this one. From now on, all of our cross sections we add, that has to be true. If one's downstream of another, its river station has to be lower than one that's upstream. Now if you see the word station, like you do right here, without river before it, what it's referring to is the distance across the channel, like on a cross section. So I have station, 0 here is at the middle of the channel cross section, and then I have the offset from the channel center, which is also my stationing. That's different than river station. So you got to be sure to keep that straight, because later on it's going to get really confusing if you get those mixed up. Alright, so our first river station cross section is 1000, and I'm going to add another one at 0. So once I've done that, I go back up to river station 1000, and then here I'm going to enter in the station elevation data from the handout. So at river station 1000, my first point is going to be -20 feet as my station, and the elevation for that is going to be 8 feet. That's the coordinates of this vertex. And then I'm only going to enter the coordinates of the vertices, and it's going to interpolate between them with straight lines. Okay? So I go back here, river station 1000, and I've got -20 and 8. My next one is going to be at -12.5, and it's at 5.5. My next one is at -5, and it's at 5. And then we've got -2.5, 3. Oops. Yeah. Is that right? I think that's right. And then I'm at about, it looks like 2. And also 3. And then I'm at about 2.5, and I'm at 4. And then I'm at 10, and 5, 15, and 8. And I'm going to apply the data. And when I hit that apply data, it's going to plot it out for me, so I can make sure that it kind of looks like what it's supposed to look like. I'm going to do the same thing for river station 0 now. My first station is -20, and the elevation is 5. -15, elevation is 1.5. Let's see, so -2.5-ish, -3, somewhere in there, elevation 1. And then I've got, actually, yeah, so let's change this one to -3, so we can change this one to -2. We'll call that 0. And then 2, 0, 3, 2, oopsies, 3, 2, and then 5, 2, 15, 5. Hit apply data. Looks about right. Alright, so now I'm going to go back to cross section 1000, and I've got some other data to fill in here. Downstream reach lengths, Manning's End, main channel bank stations, and contraction expansion coefficient. So the downstream reach length is a really important parameter. You can see this and the Manning's End are broken up into LOB, which is left overbank channel, and right overbank. I can put in different values for those. I'll talk about the overbanks in a second. It says on here that Manning's End is 0.021 in the channel and 0.035 in the overbanks. Oops, okay, that was bad. So this is Manning's end. So I'm down here, 0.021 and 0.035. 0.035. Now the downstream reach length is the place where the model knows how far downstream from this cross-section is the next cross-section. So we are at river station 1000. That means the next cross-section, which is at river station 0, is 1000 feet downstream. Pay special attention that just because I number my river stations 1000 and 0, HEC-RAS does not know that those are 1000 feet apart from that. The numbering only is there to order cross sections from upstream to downstream. I have to put in here the distance between those, okay? And for now, because this is a straight channel, I'm going to put in that the distance downstream is 1000 in the overbanks as well. If I had a really winding channel, I can put in longer lengths on the outer bank and shorter lengths on the inner bank to simulate that. But for now, we're just going to assume it's a straight channel. Now the bank stations, these are not given in here. Bank stations are things that what they're going to do is they're going to determine where this breakdown between the channel and the overbanks is. So where does the Manning's end transition from 0.021 to 0.035? Usually you can kind of see this in the cross section. If I look here, it looks like this little part right here is the main channel, and this part right here and this part right here I would call overbanks. That's where if you have flooding, the river's going to flood in over the banks, but under normal circumstances it's kind of in the main channel, and that's why it gets cut that way. So if I'm picking this as my left bank station, and that point right there is at, I think is at -5. So I'm going to put my left bank station at -5, and my right bank station here at, it looks like it's at 3. And if I hit apply data, I did something wrong. My right bank station, it's at 2.5, the way I entered it. There you go. So when I do that now, you can see these two stations turned red as bank stations, and the Manning's end is shown here as 0.035 in the overbanks, 0.021 between these two stations. And then the contraction expansion coefficients are 0.6 and 0.8. So 0.6 and 0.8. These are sort of like minor loss coefficients. They kind of simulate friction or losses associated with contractions and expansions. They're multiplied by the change in velocity heads between those two. We're not going to talk too much about them, but we're going to enter those in. And then we're going to go down to station 0, river station 0, and do all the same stuff. So it actually pulled the Manning's end values in for us, but we need to establish the left bank station, this one, which we're going to say is at -3, and the right bank station, this one, which we're going to say is at 3, I think. Let's see. Yeah. And then the downstream reach lengths, this is our furthest downstream station. So we're going to enter 0 into these because there's nothing downstream. And we're going to change our contraction and expansion coefficients. And I hit apply data. Okay. So if you're following along on the handout, we are now at letter C. So I'm going to close this. My two cross sections show up, one at 0 and one at 1000 on my reach. And now I'm going to go up to, I think it's in, is it tools? No. Tools, cross-section interpolation, and I can either choose within a reach or between two cross-sections. Doesn't matter, since those are the same for this purpose. When I hit this, it automatically fills these things in, and it says, what is my maximum distance between cross-sections? And we're saying we want that on a 50-foot interval. Don't worry about the rest of this for now, and just hit interpolate cross-sections, and then hit close. Now what you see is that when I did this, it actually interpolated all the different properties along the entire reach and created all these new cross-sections at 50-foot intervals. The ones that have the asterisks next to them are interpolated. The ones that don't, I put in. If I now go back to the cross-section editor, as I go up, I can see there are all these different cross-sections, and as I go upstream, you can see that the elevation keeps going up. Sometimes it resets because of the axis keeps changing, but there's all my cross-sections. So if I set everything correctly at the start, everything should be interpolated correctly. I don't want to forget to put in these properties before I interpolate, because it's using them. So you'll see now the downstream reach length for each of these is 50 feet, because now the next cross-section downstream is 50 feet. It changed it for me. And then of course the geometry is all changed as well. Alright, so through letter C, it says it'd be a good idea to save your geometry at this point. So one thing you'll notice is in HEC-RAS you've got a project, plan, geometry, steady flow, unsteady flow, etc. These are all different files. I started my project file, but now I could save my geometry data. And so I can just say this is, lab 6 geo. And you can see now it put that file name in for the geometry. And whatever the project is here with the different files below it, when you open that project, it should open all the different files. But sometimes I'll want to have like two different geometries. Maybe one is an existing geometry and the other is a proposed. Or later we'll talk about plans. I might want to have two different plans too. So that's why you have the ability to save different geometries within the same project. Alright, let's go to letter D. It says delete river station 5. It says 5.00. We should say 500. Alright, so what we're going to do now, all the stuff we're going to do now is associated with trying to enter in the bridge and culvert that are located on this stream. So if I go to the PDF, it has some information about those here. A gravel road and culvert are located at the midpoint of the stream reach. The culvert's 3 feet in diameter, 30 feet long, has a square-edged entrance with a head wall, lies along the channel bottom. It's circular and concrete. The end of the pipe is square cut. The roadway is at an elevation of 6 feet and has a width of 20 feet. So I'm going to scroll down here, and on the last page you can see there's a little diagram of this. So we've got River Station 550 up here. The culvert and the bridge are located at River Station 500. That means the center of them is at 500. And so we want to create this whole thing within our model. Right now we have a River Station 550, we have a 500, and we have a 450 that's only the stream, but we need to put all this stuff in so we can simulate it. Okay. So it says I want to delete River Station 500, so I'm going to go to that one, and I'm going to go up to options, and I'm going to hit delete cross section, and I'll say yes. The question it asks me is, do you want the reach lengths to be adjusted automatically to account for removing this cross section? What this means, if I say yes, then River Station 550 is going to, which right now has a downstream reach length of 50, is going to be get a downstream reach length of 100, knowing that this cross section no longer exists. So if I say yes, 550 gets 100 because the next cross section downstream is 450, right? So I said yes. Now I've done that. 4 new cross sections must be inserted, 2 upstream of the culvert and 2 downstream. insert the new cross sections, find the cross section nearest to the section to be added, and select copy current cross section. So let's go up to 550, and we're going to go options, and we're going to say copy a current cross section, and we want to copy it to two new places. Where? Well, if I look back at the PDF, I'm copying 550 to 520 and 516. And then what I'm going to do is I'm going to take 450 and I'm copying it to 468 and 484. Alright, so here I want to put 520, and I might as well just copy 520 to 516 because they're the same as 550. And then I'm going to go down to 450, and I want to say options, copy, and I want to put that at 484 and 468. 44 and 468. Okay. So, let's see. Let's go back up to 550 now. You'll see it still has a downstream reach length of 100, but if we're numbering our river stations according to how far they are apart, so our next one down is 520, which means we want only 30 feet to be in between these. So when I go to 550, I need to change this to 30. And then when I go down to 520, the next one down is 516. So I need to change each of these to 4. Now the next one downstream of 516 is 484, which is 32 feet downstream. So this one has to say 32. 484, the next one's 468. That's 16 feet. And then 468, the next one's 450, so these are 18. Okay, now everything's right for reach lengths. Now I want to, I'll be talking about in a little bit why we're doing this. Why do we need to create these new cross sections in order to simulate this? Now there's a big paragraph in the middle of the handout here at this point that I will I'll come back to in a few minutes, but it's really, really important, especially when you go to do a project on your own and you have to be figuring all this stuff out on your own when you don't have a step-by-step explanation of everything. Okay, but we need to adjust our elevations now. So what we did is we moved 550 to 520 and 516, and we moved 450 to 468 and 484, but those are all at the same elevation right now. And what we want is we want them to lie on the same slope that we established initially. But since we just copied them, the actual cross-section itself didn't shift down when we sort of copied it to a new river station. So you'll see, 550 and 520, they have the exact same cross-section. Not just the same geometry, but the same elevations. So, but we want, as water flows downstream, for it to be going downhill, so we want lower elevations as we go down. So what we need to do is, what we normally need to do is figure out what the slope was and then interpolate and so forth. What I've done for you is I've told you what to do. So river station 550, the minimum elevation is 1.65. If I go up to 550, the minimum elevation should be 1.65. When I go to 520, I want the minimum elevation to be 1.56. That's 0.09 feet below where it is right now. So what I can do is I can reduce all of these elevations by 0.09 feet all at the same time by just going up to options, adjust elevations, and I'm going to say minus 0.09. Okay. And now you'll see at 520, the minimum elevation is 1.56 feet. At 516, we want it to be 1.55. It's 1.65 right now. So we go to adjust elevations and we say we want minus 0.1. And we go to 484. It's at 1.35 now. We need it to be at 1.45, right? Because we moved this one up here. Now we need to move this one up to get it back to where it needs to be. So for this one, we need to do options, adjust elevations 0.1. That adjusts everything up. And at 468, it's at 135. We need it to be at 140. And so we're going to do this, and we're going to do plus, 0.05. Alright, so now as I click through, all of my downstream reach lengths and elevations have been corrected to where I want them. So I have completed letter D. Again, I'm going to come back to the paragraph in a bit. So I'm going to close this guy, and I'm going to hit the bridge culvert button over here on the left. You'll also note, you can see the new cross sections I added in here on the map. One little minor note, sometimes this map is a little bit buggy, where you'll make changes in the geometry editor and they won't show up here, or this will just look weird. Just note that sometimes this is buggy. It's just trying to represent visually what's in the model. It's not always correct, but if something looks weird on here, it's a good warning that maybe, or I would say probably, something is wrong in how you've defined your model, and you'll want to look into, whatever the visual clue is, look into why it's doing that. But note that sometimes it's just wrong and everything's correct. So it just means double check things. Alright, so bridge culvert editor, I get this window, and then it says I want to select add a bridge culvert from the options menu. So I go up to options and I say add a bridge and or culvert. It says enter a new river station for the new bridge or culvert. This one is going to be at 500. It wants sort of the midpoint of those two. Okay, so now at 500 it knows there's a bridge. And it says press the culvert button now. So right here you can see culvert. I'm going to click that. And enter the diameter, shape, and other requested parameters. So culvert 1, shape is circular. Its diameter is 3 feet. Okay. And then its length is 30. Says it has a square edge entrance with head wall, so that's already set. It's concrete, so that's already set. Now the distance to upstream cross section. Let's see. Sometimes when I hover over this, it says distance from upstream cross section to the culvert. I have a little note here that says, for distance to upstream cross-section, use the distance from the upstream end of the culvert barrel to the next upstream cross-section. So if I look here, and this is the center line of the 30-foot culvert, that means the culvert has 15 feet on either side. So if we're at 500 here, we go up 15, we're at 515, and 516 is 1 foot upstream of that. That means in here, distance to upstream cross-section is just 1 foot. The Manning's N is given as 0.011 for both the top and the bottom. If I just had the material, these question mark blocks sometimes will, if it's working correctly, will open the user manual and it has tables of these in it. If it's not, you can always look at the user manual online with the link given in this handout. Let's see. So Because one thing you're going to need to do is enter an entrance loss coefficient, and again that should be here, so let's see what happens. Alright, it opened it on this screen, so let's bring it over here. Entrance loss coefficient, I can scroll down, and it has coefficients for different things. This is a concrete pipe with head wall, square cut end of pipe. My coefficient is 0.5 for that. So we go back to here, and we want 0.5. And then it says, okay, so let's look at the inverts. Upstream invert elevation, downstream invert elevation. The invert is the elevation of the lowest point in the pipe on the inside of the pipe. All right, and we want these pipes, this pipe, this culvert, to be on the bed of the stream, so that, you know, flow right that's going along the bottom of the channel can go right into the culvert. So when we look at here and we see that this cross section, the minimum elevation is 1.55, that's where we want the invert elevation of our culvert to be, is at 1.55. And on the downstream side, same thing, we want our downstream invert elevation of our culvert to be at 1.45, so it's lying right on the bottom of the channel. So here I'm going to put 1.55, and here I'm going to put 1.45. For centerline stations, I say enter the horizontal coordinates of the center of the culvert upstream and downstream. Note, this is not river stations, it's what's the centerline station of the barrel. So it's looking at where in the cross section is the barrel located. It doesn't know if it's in the center or on the edge. So in our case, because our cross sections that we were given, the center is at 0 in both of these, and all the interpolated cross sections is the same thing, and we want our culvert centered on that. We're going to say that our upstream station is 0, and our downstream station is also 0. Okay, I'm going to hit OK. I want to make sure I put everything in here right. Culvert 3, circular. Okay, I got those correct. 1, 30. Yes, 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 yes. Okay, I think I did it correctly. Okay, there you go. Now it's showing up, so I can see my culvert now. It's in the right spot, lying on the bottom of the channel, centered, and 3 feet in diameter. It looks oval, but that's just because of my scale here. Okay. Now we're going to enter the roadway data, so we're going to hit deck roadway. Now this is one, the culvert editor box can be confusing to some people. A key thing they often get wrong is that distance to upstream cross section parameter and the centerline stations thing. This is probably the place where most people mess up. This seems so simple and it's very confusing. So it says to enter the roadway data, do this, and then it says distance is the distance between the upstream cross section and the upstream edge of the road. Width is the road width. Let's enter that one right now. We know our road width is 20. And the upstream and downstream stations are measured along the road, along the axis that the river cross section is on, not the longitudinal axis of the river in the direction of flow. That would be a river station. High chord is the elevation of the road surface. Low chord would be used to give the elevation of the underside of a bridge deck. But for our cases, this is an embankment that the culvert's going through, so there is no low chord. Okay. So first, distance between upstream cross section and deck. Like I say in here, it's distance between the upstream cross section and the upstream edge of the deck. So when I look at this diagram, I want my 20-foot road So 10 feet on either side of this center line. And so from 500, I'm up to 510 when I'm here, and my next cross section is at 516. So this distance is 6. So that is what I'm going to put in here for distance. Now this table, I've got these 3 columns are upstream. These 3 columns are downstream. Station is distance across the cross section, right? It's not river station, it's station. Okay, so it's saying we've got a road. We want to look at both the upstream side and the downstream side. Station across the road, and high chord elevation, low chord elevation. If our road is flat, then the upstream high chord elevation and the downstream high chord elevation are both the same, and they're the same on one side of the bridge as the other side of the bridge, one end and the other end. So what this means, and you'll see this in the diagram in a minute, I want this bridge going across here, this embankment bridge. It's at a 6-foot elevation, and it's going to start at the bank. I can enter a value that is to the left of this bank. It doesn't have to be right on the bank. So you can see here, if I enter -20 at 6 foot, it's going to start on the left side of this line, which is good. I could also enter -50. That's fine. It doesn't really matter as long as I'm to the left of this line. So upstream, I want -50, and I want downstream -50 as well. Also, I want on this side now, the x-coordinate, the station, I'm going to do the same thing. I'm going to just put 50 and 50. Alright, so it's going to draw this line across, but the high chord is my elevation of my bridge, which is 6 feet. So what I've done here is I've entered in 4 sets of coordinates. On the upstream end, which is up here, upstream, I've entered in basically an x and a y. -50, 6, 56, 56. Okay, so it's going to draw a straight line between those 2 coordinates. And then on the downstream side, which is this one, I've entered 2 sets of coordinates, -56 and 56. Okay? I'm not going to mess with anything else on this. I'm just going to hit OK. Okay, let me make sure. There you go. Okay. So now you can see it drew it in. My flat road, it's filled this in. You can see my culvert going through. It looks correct. Alright, so that completes letter G. And then I'm to letter H. From the bridge culvert data box, you can edit the cross sections just upstream and downstream of the culvert. You must set the ineffective flow areas for these 2 sections. So, again on the diagram, you can see this ineffective flow marker typical. So you've got these 4 little circles. So this gets at what we were doing with adding these 4 new cross sections. As the flow comes down here, it's filling the width of the river, but it's got to narrow down into this culvert. And so HEC-RAS has to have sort of this triangular or this like angled line that's narrowing the flow into the culvert, where in this triangle and this triangle there's not really flow occurring. Okay, so we're saying on the outsides of these 2 markers there's no flow occurring in this space. Okay, same here and same here. And you can see this in reality by these little eddies that show up in the river. And so what this will do is it'll always place the marker at the next cross section up and downstream of the culvert, and then whatever the one upstream and downstream of that is, it's going to draw this triangular line or this angled line from the river edge to the ineffective flow marker. What that means is that the distance between these 2 cross sections matters. If I put this cross section, if there wasn't one at 520 and instead it was just at 550, this line would go from my ineffective flow marker all the way up to that corner. It would be a different kind of line, and it would be a different area that was ineffective in flow. Same thing on the downstream side. If I got rid of 468 and I put an ineffective flow marker here, it would draw the line all the way up to here at 450 at the edge. So that's why I put these where they are. And going back to this paragraph, this comes this is a paraphrase of the HEC-RAS manual, and it talks about what those distances need to be. It says the cross-section just upstream and downstream should be close to the culvert, and then it says the distance between the two cross-sections upstream of the culvert should be half the channel width reduction from the upstream channel to the culvert, but could be anywhere from 0.3 to 1.1 or so times the channel width reduction. Since we don't know at the outset how wide the flow in our channel will be, we have to guess. Right? We haven't simulated anything. We don't know how wide the top width is. But in our example, I estimated that our channel will be flowing about 13 feet wide, reducing to 3 feet of the culvert. So the reduction is 10 feet, and I set my cross sections upstream 4 feet apart, 516 to 520, which is about half of the 10-foot reduction. On the downstream side, the rule is about 2 times or less the width reduction upstream. So again, if we say there's a 10-foot reduction upstream, then we use 16, which is a little less than 2 times the 10-foot reduction. As long as you're within those guidelines, you're okay. You just don't want to be kind of greatly outside of those guidelines, but there's flexibility within them. Okay, so I go back here and I'm going to go to 516. When I click on that cross section, it says select ineffective mode. I want to select my left and right stations for my ineffective flow marker. These stations are going to be on the edges of the culvert. The culvert is 3 feet in diameter and it's centered on 0. So there's 1.5 feet on the left side and 1.5 feet on the right side. So on the left, I'm going to put negative 1.5, and on the right, I'm going to put 1.5. And then the elevation, how high does that kind of ineffective flow area go? Well, it goes up until the surface of the road, because if the water can get above the road surface, it's going to flow over the road, in which case there's no longer an ineffective area kind of in that corner. So the elevations on these are both going to be 6, which is the elevation of the road. And when I hit OK, you can see it has drawn these 2 lines indicating the ineffective flow areas on the corners. Okay, I'm going to hit apply data and close that, and now it'll draw them here. That's what I want. This area is ineffective and this area is ineffective up to the surface of the road. And I'll do the same thing on the downstream side, where this is negative 1.5 and 6, and this is 1.5 and 6. I hit OK. Apply data, close that, boom. Alright, and we're done. I'm going to close that. I'm going to save my geometry. You can see now the bridge has showed up here. It's this little gray box in this map. And now I'm done with my geometry. So I'm going to close my geometry, and it's time to enter the steady flow data. So I can see these little boxes up here. This one, first one, is view, edit, steady flow data. It's got a little Q with an arrow. This one right here is an unsteady flow. So we want this one steady. So how many profiles do we want to do? We have 2 different flow rates we want to simulate. And when I do that now, on here in the reach, I've got, this is PF1, which I think stands for like profile of flow 1, and then profile flow 2. What I enter here is at river station, what's the flow rate? At river station 1000, what's the flow rate? Well, one flow profile is 20 CFS. That's my existing flow rate I was given. And the other is 100. Now the other thing I need to do in here is I need to change my reach boundary conditions. So what this is HEC-RAS is capable of calculating the depth at any point along a channel using gradually varied flow equations usually, also rapidly varied flow and uniform flow equations. But it needs to know where to start. So as it's going to start at a given depth, and then it's going to base all its calculations as what's the change in depth relative to that as I go along the stream according to all the frictional losses and so forth. So I need to tell it where to start. Now, I can set an upstream or a downstream boundary condition, and I have 5 different options here, actually 4. A known water surface elevation, a critical depth, or a normal depth, or a rating curve for each of these. Whether I need upstream or downstream is going to depend on the mode I run this in, and later I can run it in subcritical, supercritical, or mixed mode. I'm not going to get into too much about those different modes. They don't mean that you're like forcing the entire reach to be in that flow regime. What it means is basically in supercritical flow mode, it's going to start at the upstream extent of the section and calculate the depths moving downstream. In the subcritical flow routine that I could select, it's going to start at the downstream extent and then calculate the depths as I move upstream. Mixed is a little more complicated than that. I'm going to be using the subcritical flow routine. It's a little bit more stable. For this project, this example, it probably doesn't matter. But for your project, which has more complex geometry, it's going to matter. And subcritical is going to be more reliable. Excuse me. So we're going to start with our downstream, and I'm going to use normal depth as my boundary condition. So when I hit that, all it needs to do to calculate normal depth at the downstream extent is what is the slope of the channel bottom downstream of that lowest extent. It knows the slope upstream because it has all that geometry, but it doesn't have the slope downstream because it's doing this at the lowest section. I'm going to assume whatever slope exists upstream exists downstream. So when I look at this, I know I'm falling 1.65 to 1 point, actually let's look at this. I'm falling from 3 foot to 0 foot over 1,000 feet. Alright, so that is a slope of 0.003. Alright, so when I go in here, I'm going to enter 0.003 and then hit OK. And now I'm done actually with the steady flow data. I'm going to save that. Okay, it was lab 6, steady flow data. Hit OK, and you'll see it popped up here, steady flow. And I'm going to close that. And now I'm ready to run the model. So I'm going to find this little, the guy kind of walking as the steady flow simulation, walking, running. In here I can specify the geometry file I want and the steady flow file I want. If I had multiple geometries, like an existing and proposed, I could change those here. What a plan is, when I go to File menu, I can save or open plans here. A plan just matches a geometry file with a steady flow file. So I could have 2 plans if I had an existing and a proposed. I could have the existing geometry with the steady flow file that has both flows in it, and then I could have the proposed geometry with both flows in it as well, the same steady flow file, or I could change the steady flow file. But for now, we're just going to run these 2. My flow regime here is what I was talking about. I'm going to run it in subcritical, and I'm going to hit compute, and I hope this goes all through without giving me any errors. So if it says complete and there's no red text on here, it didn't have any errors. If you do have errors, you should read them and try to figure out what they're telling you, because they will give you a hint as to what is wrong. Very frequently, the 3 biggest issues are, as I mentioned earlier, some issue with the file where it's saved. something in the culvert editor, or something in the bridge editor. The two most common things are in the culvert editor, making sure that distance to upstream cross-section is correct. We had it at 1 foot in here. And in the bridge editor, that the distance one is also correct, right? Distance from the upstream edge of the road to the cross-section upstream. Or that little table where we had station and then high chord. Those three things are sort of the most common. Everything has to be right in there for the model to run. I'm going to hit close, and now there's a lot of things I can do to view results. One thing I like to do first is just hit view profiles, this little guy, and this is going to show me the whole reach, the whole profile. Right now it's only showing me PF1, which is the 20 CFS one. It's got the water surface, which is the blue line here, and it's highlighting everything below that in blue. It's got the energy grade line in green. It's got also this, well, the red line is the critical depth, I believe. So it's showing it me here in the culvert. If I want to show the other profile on here, I can hit profiles and just click on that. And then right now the axis is a little off, so I'd have to scroll up, but I think I can I change that? I hit full plot, there we go. So now I can see in flow profile 2, the water surface is going over the road. So 20 CFS we were passing through the culvert, now at 100 CFS we're flooding and overtopping the road. That's one way of viewing things. I can also look at the cross sections themselves and kind of click through them. So right now it's showing me both flow profiles, the 20 and the 100 CFS. As I get towards the culvert, you can see at the 20 it's the culvert's about half full. At the 100 it's overtopping the road. Right. So you can mess around with the different data. There's also tables we can look at of data, and you can change what it's showing you in different profiles, plans, reaches. There's lots of different settings. So I'll let you explore some of that. This actual lab handout has exactly what I want there. So read very carefully what I'm asking for, and then you can kind of find those specific plots and include them. So that concludes this lab, and good luck. And if you want, of course, you can go back and watch any sections, pause it. This will be helpful for later, the later project.